Welcome to this course, Fundamentals of Compressible Flow, in the module 4, Normal Shock Wave. We covered in last 3 lectures the following topics. So, the topics of shock waves, its formation in one dimensional medium, fundamentals of fundamental equations have been derived, and most importantly the relations that governs through Prandtl equation is also framed from these fundamental equations. Then we move to the normal shock analysis and flow property calculations across the normal shock, which uses this Prandtl equation. And having said all these property calculations, we move to a very important theorem called as Crocos theorem. This theorem talks about the fluid kinetics aspects with respect to thermodynamic concepts, and that can be correlated with for the normal shock. Now, having said all these things, we try to demonstrate the gas property tables, and these gas property tables was derived from the fundamental equations of normal shock analysis using the that are used for flow property calculations. In fact, this gas property table can be considered as a database or data set to find out the flow property that are prevailing across a normal shock. So, these are the very basic topics that were covered in this normal shock. Now, in this lecture we will try to justify certain important facts with respect to the shock waves as a compression device. So, what we have seen here is that always there is a steep pressure rise across a normal shock. So, the question arises, can you think of the shock wave as a mechanism to compress a gas? Can it be it will be effective? So, all these things we will try to answer by considering the fundamental thermodynamic aspects, that is with respect to isentropic compressions versus shock wave compressions. Now, when you deal with these isentropic compressions, normally there are standard thermodynamic relations that are available, but we do not know the thermodynamic background, although we found out the flow property, but we do not know the thermodynamic background. So, for that a relation which is derived, which is called as Higuiot relations, and in fact this forms the basics of thermodynamic concepts that happens the pressure rise as a across a shock wave. And using this relation one can find out that how a shock wave compression mechanism can be understood thermodynamically. Okay. So, before you move to this shock wave analysis of compression, so let me give some very basic background of thermodynamic analysis of a compression process. We all know from the beginning of thermodynamics course, we used to have a very simple concept of using a figure considering a piston cylinder device in which gas is contained, and the piston movement when the gas is supposed to be compressed, the piston has to move towards the dead end of the cylinder. If the gas has to expand, the piston has to move away from the dead end. So, this is the way we can make this gas to compress or expand. Now, in fact, what we can say is that this cylinder, the gas which is there in this cylinder has change in the specific volume or density when the pistons moves in and out of the cylinder from the dead end of the cylinder. So, we view this method to be a compression or expansion, and in fact, many times we can also make this system as and while the motion of the piston is motion of the piston is regulated in this cylinder, we can say there is a work transfer in terms of PDV work. And other analysis we could perform that one can add heat into this gas and thereby see what happens to the piston movement. So, there are multiple ways one can handle this particular thermodynamic aspects of this piston motion inside the cylinder. So, such a process are generally given names. Those names we can call this as a constant pressure process or isobaric process, constant volume process, isochoric process, constant temperature process, isothermal process, constant entropy process, isoentropic process. And all these four processes can be thought of occurring in a very steady state manner and in a very small or we can say in a very quasi static manner, so that the process can be thought of happening in a reversible way. But other process that may not be a reversible, we call this as adiabatic process, where there is no heat additions. That means, this cylinder does not encounter any heat interaction. So, this is how we handle this motion of the piston inside the gas. Accordingly, we assign different thermodynamic processes. Now, when all these processes, we call them as a polytropic processes. So, when I say polytropic processes, we can say this and if you try to plot the pressure volume diagram. So, normally we call this as a PV diagram, pressure and specific volume diagram. So, this process we say it is occurring in a polytropic manner, where P V to the power n is equal to constant. So, when this by following these equations, the pressure volume relation is considered. Now, let us see that what does this mean. Now, when n is equal to 1, so when n is equal to 0, so it is like P pressure is equal to constant. So, there is no change in the pressure. So, we cannot recognize it to be a compression process. But apart from all of the n is equal to 0, for all other values of n, we can say that when there is a decrease in the specific volume, the pressure always increases. So, when now the value of n essentially decides the how a process can occur in a very slowest possible manner. When we are occurring the process in the slowest possible manner, then it will be very quasi static in nature, and the conditions of maintaining the reversible nature will be assured. So, as and when we move n towards off, the process occurs in a very slow manner. So, let us say when n is equal to 1, So, this process says P v to the power n is P v is equal to constants, and this relation is true for isothermal process. And when n is equal to let us say in a constant pressure process, we can say its n is equal to 0. In fact, it is no longer a compression process, and in a constant volume process, that is the other limit where this compression process happens to be a vertical, very step manner. So, it is a constant volume process. So, here n goes to infinity, but any other value of n makes this curve to be steep. Now, let us say that when we are undertaking a compression process through for a certain change in the pressures. So, if say P 1 initial state and P 2, and if at all I want to do this compression process, then if I start from n is equal to 1 means isothermal process. So, if the initial state we can start from 1 and final state ends at 2. So, I can go in a slowest manner, that is in a isothermal process. Similarly, keeping increasing n further, the curve becomes steep, but what the basic condition is that the work transfer, which is essentially quantified, that area under the diagram, comes down if you brings the curve becomes steep. Okay. Now, in particular when we have a constant entropy process which is isentropic. So, there it is nothing but the reversible adiabatic process. So, there n becomes gamma, that is specific heat ratio. So, somewhere for air this becomes 1.4, somewhere we can have another curve which is just close to n is equal to 1. So, this you can say n is equal to gamma. So, normally we can say roughly an isentropic process will be somewhere in this manner. Okay. But when we say another process which is called adiabatic, so this need not have to be reversible in nature. So, although we can say gamma or n is equal to gamma is equal to 1.4, but the process is irreversible, whereas this is a constant entropy process, this is reversible in nature, which means while going from 1 to 2, I can come along the same path while in return with very minimal loss. So, this is how we view this compression mechanism in a PV diagram. So, with this background, let us see that how I can incorporate a shock wave as a compression device. Does any of the relations suits to me or not? To do this analysis, let us see that when we undertake a compression in a shock waves, so we say there is a standing normal shock. So, across a shock wave the Mach number drops, but your static pressure P 2 always rises, but in a very steep manner. Now, one angle we can give this to this particular problem, and obviously this process cannot be considered as any of the quasi static process, because this jump is very instantaneous or very steep, and this happens in a very short test time. So, none of the quasi static process will follow. Then even it cannot be also considered as an isentropic, because entropy always increases across the shock wave. But one more realistic way of looking at this problem, because when you derive this normal circ relations, we say that it is a, you can say there is an imaginary duct consisting of streamline, but that duct is adiabatic duct. Adiabatic duct means there is no heat interaction into this medium. So, to some extent the process will be an adiabatic process, but even then, even though although a process is adiabatic, whether we have to really dependent on the specific heat ratio gamma or not, that becomes still a question mark. So, all this analysis we are trying to see that if we can give a thermodynamic meaning to this compression process. So, such a thermodynamic meaning we can give through an relation what we call as Higoniot relation. So, what it says is that till this point of time, we always talk about normal circ from its analysis, the relations, flow property calculations. For the time being, let us see only thermodynamic aspects of increase in the pressure, and whether we can say that this increase in the pressure can have any thermodynamic link. So, this is the entire motive of this analysis, and so what we say here is that changes across a normal circ can be independently assessed purely on thermodynamic aspects, that is without involvement of any reference velocity of Mach number, because in all earlier analysis we used to say for different values of Mach number, these are the property ratio, static P 2 by P 1, T 2 by T 1 and so on. But here you will say that without involvement any velocity of Mach number, how we can give a meaningful thought by, and that equation is known as Higoniot equations. And these Higoniot equations can be derived from the basic governing equations for one dimensional flow prevailing in a adiabatic duct. So, and this equation has a great resemblance to the first law of thermodynamics for an adiabatic process. That is what the process or mechanism of shock wave, since we follow to some extent, we say that it is a adiabatic duct because there is no heat transfer involved. So, with these logics we can say the process is in adiabatic nature, and when Higoniot equation is formed, we can say that it has a definite link to the first law of thermodynamics. So, to do that, to do this analysis, so let us revisit the governing equations of normal circ, which is continuity, momentum and energy equations. So, continuity equations, we say it is rho 1 u 1 is equal to rho 2 u 2, momentum equations is p 1 plus rho 1 u 1 square is equal to p 2 plus rho 2 u 2 square, and energy equation we are writing in this form, that is E 1, that is internal energy, E 1 plus p 1 by rho 1 plus u 1 square by 2 is equal to E 2 plus p 2 by rho 2 plus u 2 square by 2. Why we bring this internal energy concept here? Because in the beginning of analysis of normal circ, we defined that entire flow kinetic energy due to high speed nature immediately, because what we told that after this normal shock the flow becomes suddenly subsonic from its supersonic value. So, the kinetic energy, whatever kinetic energy of the flow it has in the upstream, all of them gets converted to internal energy, thereby increasing its temperatures. So, what we say is for this condition 1 and 2, P 1 and T 1, and here P 2 greater than P 1 and T 2 is also greater than T 1. So, internal energy E 1 and E 2, So, normally this E 1 is nothing but C V times T 1 and E 2 will be C V times T 2. So, there is a rise in the internal energy. So, that is what these equations are reframed in this manner. So, now let us re-look into these equations, but in a different context. So, from continuity equation or so from this continuity equation, one can rewrite u 1 in two ways. I can write u 2 is equal to u 1 into rho 1 by rho 2, or I can also write u 1 is equal to u 2 into rho 2 by rho 1. Okay. So, now let us take that we take only this expression and substitute in momentum equation. So, this we get from continuity, and we substitute that thing in momentum equation. So, when I substitute this in momentum equations, that is u 2 in the right hand side. So, we get P 1 plus rho 1 u 1 square is equal to P 2 plus rho 2 u 2 square. I put u 1 into rho 1 by rho 2 whole square. So, we simplify these equations and solve for u 1 square. So, how do you do? So, you can bring this particular term the other side, like rho 1 u 1 square, or you can bring this particular term in the left hand side minus rho 2 rho 1 u 1 square minus rho 2 rho 1 square u 1 square by rho 2 square is equal to P 2 minus P 1. So, rho 1 u 1 square you can bring that common. So, you can say 1 minus rho 1 by rho 2 will be P 2 minus P 1. So, ultimately we can write this equation as u 1 square is equal to P 2 minus P 1 divided by rho 2 minus rho 1 into rho 2 by rho 1. Okay. So, this is why we get from momentum equation. Similarly, when you put this u 1 in the momentum equation's left hand side, then we can also get u 2 square will be equal to P 2 minus P 1 divided by rho 2 minus rho 1 into rho 1 by rho 2. Okay. So, now we have two expression u 1 square and u 2 square. So, now you substitute u 1 square and u 2 square in energy equation. So, when you do that, we arrive at this particular expressions, and we do and simplify, then we arrive at this particular expressions. What it says is that the left hand side of this expression, it is E 2 minus E 1, which we say is that change in internal energy. So, change in the internal energy across the shock wave, that is equal to the P 2 plus P 1 by 2 into V 1 minus V 2 by V 1 minus V 2. Now, expressing this specific volume into density, one can write 1 by rho 1 minus 1 by rho 2. So, this is how we say we can write this particular expression. Now, if you give a little bit of thought, assuming that in normal sequence, when we calculate the average pressure, normally we add up all the pressures and divided by the total numbers of turns we are going to add. So, here there are two pressures. So, we represent this as V average into minus delta V because the volume the density increases, the specific volume drops, that is a minus. So, we say there is a, so this is a, what we say is a, so across this shock wave we say there is a step change in internal energy. Now, if you, this is what we see in the across the shock wave. Now, let us see the first law of thermodynamics. So, in a first law of thermodynamics, in a differential form, we write dE is equal to dQ minus P dV. Now, in a situation when the process is an adiabatic process, this term we can neglect, so that we can see this is minus P dV, pressure times dV specific volume. Now, if you look at these two equations, so this is for a differential form of internal energy, and we see that there is a great resemblance between these two terms. Of course, the only difference that we have here is that here the change is a very finite, but its change is we are represent in a very in a differential form. So, that is what it is written here, that it has a great resemblance for first law of thermodynamics for an adiabatic process, that is the change in internal energy is equal to change in the specific volume multiplied by mean pressure across the shock wave. In fact, this relation was derived is true for all the thermodynamic processes, and that holds good across a normal shock. Okay, this since this has nothing to this, since we did all these things from this basic fundamental equation, it is true for all types of gases, real gases, chemically reacting gas, perfect gas as well. So, this is again another way of interpreting these Higgins-Newt equations. So, basically we framed this equation from this our analysis, that is change in internal energy, and it is represented through these Higgins-Newt equations. Now, in this equation we will try to see that these relations, when you do it for perfect gas, when you recall that for a perfect gas and calorically perfect gas, we can write E is equal to Cv times T, and Cv is equal to R by gamma minus 1, T is equal to Pv by R. Now, when you put all these relations, this Higgins-Newt equation forms this fundamental is the Higgins-Newt equation turns out to be a pressure volume relations between two thermodynamic states. So, here two thermodynamic states are 1 and 2, like the pressure ratio across this we are now representing specific volume, like here if I say P1, pressure is P2, corresponding specific volume is V1, and in fact that is nothing but 1 by rho 1, and corresponding specific volume after this normal shock will be 1 by rho 2. So, what it says is that the pressure ratio are now expressed in terms of specific volumes for a calorically perfect gas. So, here, so that is what I can say, that is pressure volume relation across a, that is Higgins-Newt equation represented as pressure volume relation for a normal shock. more specific, it will be specific volume, pressure specific volume relation across a normal shock. So, now let us see how these Hugoniot relations has a great significance for our understanding. So, for that we will now talk about its inferences. What does it signifies to us? So, if we recall this particular equation in a very generic way of thermodynamic analysis, one property can be represented to any other independent parameters. For example, I can say internal energy as a function of pressure and specific volume. So, this is as per the thumb rule of any thermodynamic property can be represented in other two independent parameters. And in this case your change in the internal energy is related to pressure and specific volume through this Hugoniot relation. So, in other words, I can say that from using this equation I can express this P 2 as a function of P 1, V 1, V 2 and E 1, and how this functional relations forms. One of the functional relation is this E 1 square expressed into as a function of P 2 minus P 1 as a function of P 1 and P 2. So, this functional relation has can be exactly defined by these Hugoniot equations. So, from this one can find out what is the pressure P 2 as a function of P 1, V 2, V 1 and E 1, P 1, V 1, V 2 and E 1. So, what it physically means to us like that, suppose you have the given conditions or known condition are P 1, V 1 and U 1. This is normally known, that is upstream condition, and downstream condition we can say that we can calculate P 2. How? By using, but what the condition you require? If you know one of the particular conditions V 2, then in fact we will just for the time being we will not talk about the Mach number. So, instead of Mach number, if you know only the specific volume in the downstream condition, then one can correlate P 2 as P 2 with the knowledge of P 1, V 1, V 2 and E 1. So, this is also in similar context. In earlier situation we were talking in terms of Mach number, here we are not talking in terms of Mach number, rather we talk about with another known parameter, and in this case is the specific volume. So, this gives a curve which is known as Hugoniot curve. So, what it means is that at equilibrium conditions, the property value of thermodynamic state can be expressed as a function of other state variables, and in this case for a given upstream conditions for a normal shock, that of pressure, specific volume, velocity, the Hugoniot equation, that is this, gives the relation for downstream parameters of pressure and specific volume. So, downstream parameter of pressure and specific volume can be found out. So, one can find generate a plot known as Hugoniot curve, and this curve is nothing but the locus of all possible pressure and specific conditions across a normal shock. So, means if you know these known conditions, one can generate a lot of data by just imposing some numbers to this, and all of them will decide about the possible flow conditions across a normal shock. And in fact, the depending on the strength of the normal shock, these numbers will vary. So, that means this locus of all possible pressure and specific conditions of normal shock various strength can be found out for one specific upstream values. So, to start this, so one can say that one can draw an Higgs curve of like this in a pressure specific volume diagram. So, for different values of U 1, P 1 specific volume, one can find out all possible numbers. Now, when I say, so if I say now point next question arises, where is this initial point? So, if you look at the initial points, the initial point should be corresponds to 0 entropy as if the flow was isentropic. So, S 2 was is equal to S 1, that means your initial point initially if you start from this particular point. So, initial point P 1 and P 2 as if there is no compression process just initiated. Now, if I want to think about you bring the non isentropic nature through a shock wave, then I can say the point 2 will proceed along this curve in these directions. Now, when I move this direction, I can bring this process through a Higgs curve. So, I can say 2 can lie here, 2 can lie here, 2 point can lie here. So, any point we can draw this. So, all this point is nothing but the all possible conditions of a normal shock. In fact, I can start the point 1 instead of 1, we can start a point somewhere here, let us say 1 dash. So, correspondingly this point can be a 2 dash or this point can be a 2 double dash. So, likewise all possible conditions one can generate. So, point 2 will move towards left. Why left? Because the pressure should increase, and corresponding y axis we will talk about what pressure we are supposed to get. So, on this Higgs curve we can say any 2 points on this Higgs curve we will talk about the pressure jumps across a normal shock. So, this is how it is explained that the locus of all possible physical states occur only in the upper branch of the Higgs curve, in which initial Mach number is either larger or equal to unit. That means, I cannot. So, this direction of movement is not possible because it will lead to an expansion, not a compression. So, it cannot be possible because it will be impossible situation and shock wave will not occur. So, that means in other words shock waves flow can occur that are initially supersonic. So, all these points will lie in the supersonic region. Now, to bring more clarity into this, that how exactly I will locate the point 2 on this curve. So, let us revisit these equations of Higgs relation, that is P 2 minus P 1 divided by V 2 minus V 1 is equal to minus U 1 by V 1 square. So, if you look at this normal shock wave, what does this normally mean? U 1 and rho 1 is nothing but the velocity and density, that is nothing but 1 by specific volume V 1. So, mass flux I can say rho u is equal to constant, that is rho 1 u 1 is equal to a constant quantity. So, I can say this as mass flux per unit area, that is known as the mass flux per unit area, because area term is, you can say it is a per unit area. So, which means that, or in other words I can write this is nothing but U 1 by V 1. So, this is also represented in this as mass flux per unit area. So, now we give this gives a logical meaning that the right hand side of this equation is the nothing but the mass flux per unit area, which is normally known for a normal shock, and left hand side of this equation is nothing but slope along this curve. So, means that if you know the mass flux per unit area, then you also know the slope. So, one can calculate the slope, and this negative slope will take you from point 1 to 2. So, in other words, what it means, if you for a given condition 1 which is located here, if I know this particular number u 1 by v 1 square, and by taking this negative slope, if I draw a line, then it will cut this point at point 2. So, this particular slope is nothing but u 1 by v 1 square. So, I have to put minus because we are moving towards the negative specific volume directions. And if I for another situation of u 1 v 1, if I can I can draw another line from this point which may take me to another point of 2 dash for different values of u 1 and v 1. So, likewise, any number of states that is possible for given state 1. So, for given upstream conditions, different states of 2, 2 dash, 2 double dash is possible. So, that means the straight line can be drawn that will intersect the Hugoniot curve at point 2. Okay. So, now when I join this line 1 and 2 in this Hugoniot curve, so this line is known as Rayleigh line, because it gives the it is drawn for a particular mass flux. And in fact, I told that the slope the downward slope of the Rayleigh line is not possible, because we cannot go below this line. So, that means if I start from the point 1, I should proceed in these directions, upward directions. So, downward slope is not possible. In this way, we can say all thermodynamic states across a shock wave can be located graphically on a Hugoniot curve. So, having given a name as Hugoniot curve or simply H curve, we are now able to see that whether I can compare this particular shock based compression to an isentropic compression. So, for an isentropic compression, I can say this process is reversible adiabatic. So, you can say P v 2 to the power gamma is equal to constant, or P 1 v 1 to the power gamma is equal to P 2 v 2 to the power gamma. So, I say it is a reversible adiabatic process, and this is nothing but we say H Hugoniot equation. So, this is what we say an isentropic process is governed quantitatively, and the Hugoniot equation governs the shock wave compression quantitatively. So, when I compare both these two equations, I can judge the effectiveness of shock wave compression with respect to isentropic compression. So, to do that, one interesting thing what we can say that we can bring a concept as shock wave as a compression device. So, what I did is in the same Hugoniot curve, I superimpose this isentropic curve. That means, when I am starting from same point 1 and I try to go on a Hugoniot curve, that is dotted line, and from same point I also can start my compression journey in the isentropic curve. So, let us see what how I can do that. So, what you see is that in the initial phase you will see that both the dotted line and solid line, they are more or less same. Now, once you proceed further, I mean once the specific volume decreases at a faster rate, then we see that the gap becomes higher and higher. So, what is seen, and for me, for instance, if at all my point 2 lies here, I would have reached a pressure P 2 if I go on a Hugoniot curve. So, my compression, that means delta P on a Hygonoid curve would have been P2 minus P1. That means, pressure rise on a Hygonoid curve will be that is on the H curve would have been P2 minus P1. But for same specific volume, if I would rather choose an isentropic curve, then I would have landed up for same specific volume V2, I would have landed up at point 2 dash. So, my delta P dash would have been P2 dash minus P1. So, this is how we say it is an isentropic curve. Obviously, we say that delta P dash is less than delta P P, which means that isentropic curve gives a less compression for same specific volume change. Isentropic gives less compression than the Hygonoid curve. In fact, this gap will become more and more if you climb on a Hygonoid curve, or in other words, at higher value of specific volume rise, the Hygonoid curve climbs over the isentropic curve. So, this is the key point of the Hygonoid curve analysis, that says that a shock wave compression is a shock wave can be a thought of a compression device. So, this is how I have explained so far, that how a shock wave as a compression device can be interpreted. I mentioned that with decrease in the specific volume, rise in pressure in isentropic curve takes place in a reversible manner, where pressure rises instantly on a Hygonoid curve. With decrease in the specific volume, the Hygonoid curve climbs above the isentropic curve. That means, it generates a high pressure. The same thing I have explained here, and this is how the isentropic curve is governed, P b to the power gamma is equal to constant, whereas the pressure rise across a shock wave is governed through Hygonoid equation. So, one can make summary of this analysis, that why a shock wave compression is a effective method. So, the one of the key point is that for a given decrease in the specific volume, that is V2 minus V1, the shock wave creates higher pressure rise increase than the isentropic compression. So, this is a one of the catch point, but there are some side effect, is that the shock wave compression is less efficient than isentropic compression, because we have seen that it is a non-isentropic process. So, it involves increase in the entropy and loss of the total pressure, which we already view that across a shock wave total pressure drops. So, this is also a negative side of the shock wave compression, but the many a times the jump, the quantum of jump that we get through shock wave compression is such a significant, that it gives a new thought as a mechanism of compression device. In fact, this particular concept has created the evaluation of next generation of height split flights, which we normally call them as ramjet or scramjet engines. And these engines in fact have very minimal use, there are very minimal use of rotating or mechanical components. So, all these engines are governed, the entire compression process in this engine is mostly governed through shock based compressions, and this shock based compression does not require any mechanical or turbo machine or rotating components. Many times what happens, that when you travel faster, the mechanical components, the limit of mechanical components, the structural limit of mechanical components, the thermodynamic limit of mechanical component does not allow to move faster. But here it is not that aspect, rather the engines can be thought of thought of to be controlled through shock based compression process. So, this is how the shock based compression is has a great resemblance or a significance for new generation evolution of flights. So, with this I conclude this module, that is on normal shock waves. So, in this module the learning components what I can frame out is some of these learning components are listed here. So, at the end of the module one should understand the phenomenal effect of normal shock, its fundamental equations, the relations that governs the normal shock, how the property flow property is calculated across normal shock. Apart from this, we bring out two important concepts in this normal shock analysis, that is Crocos theorem that talks about fluid kinematics, that means fluid flow, the flow across a normal shock is highly rotational, and also the Sigonier curve that talks about that shock wave as a effective compression mechanism. Now, apart from that we demonstrated a gas property table for normal shock relations. So, at the end of this module one should understand all these learning components and brush up his knowledge whether all these components are learnt properly or not. So, with this I will conclude for this lecture. Thank you for your attention.